All right, Jonathan. On 3, 2, 1. 3, 2, 1. Welcome, everyone. Welcome to our final review session. Final meaning two things. It's the exam for the final review, and this is our last review session for our course circuit. So this is April 30th. We're in the spring semester 2018. Our goal for tonight is to go through one final exam so you can see the whole course in its entirety. The exam we're going to go through, I think, is a really good one. It's posted on the course website, and it's spring 2014. Now, there's one thing I have to add. If I remember correctly, this final exam does not cover second-order systems. And in the past, some colleagues thought, oh, if it wasn't mentioned in the review, then it's not going to be on the final. And they didn't cover second-order systems in their studies. So I'm making it a point. I've not yet made up the exam. But I think at the very minimum, you should know for the final exam from the spring 2014, plus go back to, I think it was exam 2, and look at our second-order systems. Make sure you can do a second-order system. There were multiple versions of exam 2, I think it was, that had second-order systems on it. So Brittany, know how to do both. Okay? So that will take care of second-order systems, plus of the final exam here tonight. That's a very good beginning. Okay? All right, good. So my colleagues here, and there's 3, 4, 5, 6, 7, 8, 9, 10. 10 of us. I think I know everyone's name. I'm quite excited here. There's 10 of us here tonight, not counting myself, makes it 11. So let's go and see if we can go through this exam. So we're going to start with final exam, spring 2014. We're going to look at the exam problem by problem. And the first one says, okay, refer to figure 1. And note there are no numerical answers given, values given. Your answers should be in terms of the network elements. I'm thinking, Tara, this is an amplifier problem before I even look at it, because I'm thinking V out over Vs. So my colleagues, let's go and look at the other handout that has the figures. Amplifier problem. Chapter 1. A good way to start the final exam. So my colleagues, I'm giving people a moment to write all this down. Parker, of little interest in my life, just so you will know this also. I was asked today to be the faculty advisor for the chess club. I'm very happy. So good.
Did they just get approved?
No, they've had a chess club here for years. I see them on Friday evenings.
Oh, yeah, they've been around for years.
In the Babbio Center, I think, they normally have a room on Friday evenings and they have games, competition. So. I asked who the other faculty advisor was, and they didn't know. So I think it's been a little bit of a gap. So, all right. Let me just go back to the first question so I can get started, and then I'll bring back the figure again. First question is V out over Vs. Okay? So V out over Vs. All right. Now, we're thinking back to the February time frame when we had our first exam and our very first review together. This is from the February time frame. And what we need to do is to have a strategy to approach. So I look at this and say, I want V out over Vs. Now, we can start on the left side or the right side. Remember how this circuit works? All the current on the left stays on the left, and all the current on the right stays on the right. So this is all written up. You'll see it. But let me see if I can do it really quickly on the board here. Tell you what, R5 and R6. Let's call that REQ right. Okay? Now, how do I get V out? I think I can use voltage division. So V out will equal Req right, R-I-G-H-T, divided by Req right plus R4. And this is all going to be multiplied by A V in. Okay? So what I have is I have an expression now for V out over V in. But I want V out in terms of Vs. So Jing, what I'm going to do is I say, where's Vs? Vs is here. So now I jump, Brittany, to the left side of the circuit, and I think I can do another Req. So I'm going to call this Req left. And again, I'm going to do voltage division. So what I get is an expression for V in. Okay? V in, let me just get an eraser. Sorry to cut in front of the screen. I'll walk back. Let me write this a little neater. V in. Okay. And I'm going to use voltage division R2 and R3. And Michael, my good man, we're doing the spring 2014 exam, final. And I'm going to look at V in, and I'm saying R2 and R3, let's call that Req left. So what I get is Req left over Req left plus R1. Okay, so that now gives me the ratio, and I multiply all of this by Vs. Now, as you'll see when I get to the solutions, what we do is I take this expression right here for V in, and I plug that in here. And then I get, Michael, V out in terms of Vs, which is what we're looking for. A is the voltage source here, Michael, A times V in. No worries. No worries. So Tara, that's going to be the approach. All the math is worked out in the solutions, which we'll now look at. So Jing, I'm going to run over here to the solutions. And the math is all worked out here. So the first thing, okay, in the solutions, I started on the left side. Maybe that was good, because then, Parker, you saw me start on the right. You can also start on the left. It doesn't matter. So we get V out over V in. No, I think I started on the right. Forgive me. R5 and R6 were on the right, weren't they? Yeah, sorry. Okay. So I got the R equivalent, and we use voltage division. So this is Req over R4 plus Req times AV in. That's exactly what we have here. I just put in for Req. So then I can write that as V out over V in. But that's not what I want. I want V out over Vs. So I now go to the other side, and I'm now about to get this bottom equation here. So I get the bottom equation there as product over the sum for R equivalent, again using voltage division. I get this relationship here, which, my colleagues, is this relationship right over here where I'm walking to the board, Req left over R1 plus Req left times Vs. And I now have an expression for V in over Vs. And what we can now do is just multiply those two expressions together, or, as I pointed out over here, you can just substitute it in. Either way you see it is fine. I can substitute in for V in, or I can say I have V out over V in times V in over Vs, and I get V out over Vs. So that's the first part of the first equation. First part, pardon me, that is the first part of the problem. All right, that was the answer. Let me pause. Parker, help me out.
Would we
I don't know. What do you think? What do you think we should do, Parker?
I think if you label REQ, what REQ is.
Yeah, that's what I was thinking. Do that, but then put like REQ left is equal to.
All right, so, but Parker and my colleagues at home, can we have an agreement? If you do that, don't put REQ way up on another page. Put it right next to the answer, because we got a time constraint to grade all of these quickly. So does that sound, so you can do that as long as on the very next line you tell me what REQ left and REQ right is. Fair deal? All right, good. All right. My colleagues, that's part A. Tara, I don't know if we get up to Z on this. I don't think so. I don't think so. Okay, part B. All right, so the input resistance of this amplifier is defined as V in over I in. Determine an expression for the input resistance. Now, we've never covered this. I don't know. Where is this question coming from? Let's see if we can figure it out. So what I need to get is a relationship for V in over I in. So my colleagues, if you go back, and I'll put it up in a moment, this is the figure for the left side of the circuit. Okay? This is the left side of the circuit. Just to confirm that, we go down here and we pop open now the left side of the circuit. Now, by the way, why am I looking at the left side of the circuit? Because Alexis, I'm told to get V in over I in. They both occur on the left side of the circuit. So I now just redrew, pardon me, I redrew the left side of the circuit. And this is what I have. And what I want is V in over I in. Well, here's V in, and here's I in. Now, once again, we have two resistors in parallel, and I'm hearing Michael very softly, REQ, REQ, is speaking to me. So, REQ, REQ, see? It's speaking to me. Scarily, but it's speaking to me. So, my colleagues, I now determine REQ, product over the sum. What I now have is not two resistors, but one. I think I can now find an expression for V in easily. So let me see, there's a couple of ways of doing this. We now have V in equals I in times REQ. Now, my colleagues, help me out. Let me scroll up just a little bit. Make sure this makes sense. Okay. I in is the current up here. We now have an REQ, so instead of two resistors, I have one. What is the current through that REQ? I in, because there's only one resistor. So V in, which is the voltage across REQ, is I in times REQ. I'm asking for V in over I in. That is nothing more than REQ. Whoops, I beg your pardon. And I write then there that R in is REQ, and I write it as Parker and I were suggesting, R2, R3 over R2 plus R3. That's part B. How am I doing? Easy, all right. All right, good. So we're up to part C. We can now see one of the nice things about a final is I can combine problems. This now becomes a Thevenin problem. So now we say, okay, a load resistor is placed between terminals A and B. We want to select, Alexis, the load resistance. Here it comes. Maximum power. Ding, 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 ding. Whoop, whoop, whoop. Alert, alert. Thevenin problem, Thevenin problem. So we now have a Thevenin problem here for part C. Determine an expression for the load resistance for maximum power transfer. Okay? Now, what do I know? Michael, you know this. Michael knows this. Parker knows this. For maximum power transfer, our load have to equal our Thevenin. Now, Tiger, let me just go back for a moment to make sure I know where this is being added. This resistor is being added between A and B. So right here, I'm adding a load resistor, and for maximum power transfer, this load resistor has to equal R Thevenin. Now, how do I get R Thevenin? V open circuit divided by I short circuit. Okay, so V open circuit divided by I short circuit. So I say, okay, I now know that what I need to get is V open circuit divided by I short circuit. Now, V out, oh, wait a minute. That's what we have right over here on the board. This is V out over here. V out is REQ right over REQ right plus R4 times AV in. So I already know what V open circuit is. V open circuit is what we called in part A, V out. Okay. So that then becomes V out. And my colleagues, what else do I need to calculate? I short circuit. Now, I am hoping you remember this. Remember, for determining R Thevenin, we got to solve the circuit twice. We already have V open circuit. Now, what we need to do is put a short circuit here. Okay, put a short circuit here. And now I need to determine the short circuit current. Okay, I need to put a wire here, a short circuit, and now determine the short circuit current. I think I see it. Before I get there, though, Michael, help me out.
You take the REQ of all the resistors, and then the open circuit voltage is just the voltage to that single resistor?
No, help me out, Michael. You're talking about V open circuit, I gather. Okay, Michael, stop me if I misunderstood your question. This is V open circuit. I take an REQ here. We called it REQ right. This voltage is only across this REQ, not across R4. So I don't take the REQ of everything. I just take the REQ of these two resistors in parallel. And then if I could walk over here to the board and point out something, Jonathan, my colleague, I'm sorry to bother you. If I'm going to run over here, Michael, what happens now is I just do voltage division. So it's REQ right over REQ right plus R4 times the voltage source, which is AV in. That's how I got V open circuit. Michael, did I do okay? Thank you. Now, Michael, I think you might have been also pointing out about I short circuit.
Yeah, that's what I was talking about.
Michael, forgive me. Now, be careful. If I put I short circuit here, what's the current through R5 and R6? Zero.
So it's just going to be the current through R4.
Right. Michael, you said it right. Forgive me for not following you. I short circuit here means there's no current through R5 and R6. So what we get is it's V equals IR, so I is V over R. I short circuit is AV in over R4, which I think is what you said. Forgive me, Michael, for misunderstanding you. Are we solid? Okay.
I messed it up.
All right. So I short circuit is AV in over R4. So I say R load equals R Thevenin, and that becomes V open circuit divided by I short circuit. A little bit of algebra, and we got the result here. Now, Parker, in a case like this, you should at least cancel out the AV-ins. And if you left it like this, in fact, it's very easy to do this, right? You just bring up R4. There's really no algebra here at all. All right. Are we good? That's part C. Was that it? Yes. Oh, Tara, I'm sorry to disappoint you. All right. All right. In a moment, I'll put up figure 2, but let me just read this. Oh, I see switches. Ah, write the first order differential equation for the capacitor V sub C in standard form, V sub C of t in standard form. I say, oh, this is a chapter 4 problem. Now, where is my cursor? Right, there it is. All right, so now we're on to figure 2. I'll give you a moment to copy it. My colleagues at home, I'm just giving people a moment to copy this down. All right, I think you're pretty much set. So I see switches, and I see a capacitor, I see an inductor, voltage source, and a current source. So I'll come back to this figure in just a moment, but the first part of the question says, write the first order differential equation for the capacitor voltage V sub C of t. So I now look here, V sub C of t. So I want this for t greater than 0. So Parker, help me out. T greater than 0. This switch is closed. Alexis, t greater than 0. This switch is open. I want the voltage across the capacitor. If this switch is open, everything to the right of this switch is not important for us right now. So I'm going to redraw the circuit with R1, R2, R3, and the capacitor. That now becomes the circuit for t greater than 0. So if I go to my solutions, and notice the first thing I do is to redraw the circuit so I know what it looks like. Now, my colleagues, let me just go back again to the original figure, because someone came to my office hours today with a question as to how do I know which side of the circuit to work on. Let me make sure I describe this clearly. My colleagues, from reading the problem, we want V sub C of t. I want it for t greater than 0, according to the problem. For t greater than 0, switch 1 is closed, so all of this is connected. But switch 2 is open, so all of this to the right is gone. So then, to make sure I don't make a mistake, I redraw the circuit as part of my solution to make sure that I got exactly what I need to do. Now, I'm going to use nodal. It's shouting out to me here. All of this is one node, and I'm now going to put myself in the node for maybe one of the last times together. And now we're going to figure out the currents leaving this node. So now we're going to do nodal. My colleagues, I'm hoping this brings back fond memories. So this is V sub C of t up here. So V sub C of t minus Vs over R1. That's the current through this branch. Parker, I then want the current through R2, and then the current through R3. it's v sub c of t over r2 plus v sub c of t over r3. Then, for one of the last times together, we'll be chanting the I through the current through the capacitor, I equals C dV dt. So I then get C dV dt equals 0. I know you can do this. You know how to put this into standard form. You want a 1 in front of the non-derivative for first-order systems to be in standard form. So what I do is I gather terms. My colleagues, this might be hard to follow here, but I know once you get this first equation here, the rest is algebra. I know you can do this. I just factor out the term v sub c of t. I get 1 over r1 plus 1 over r2 plus 1 over r3, then plus the c dv dt, and it's vs over r1. That's this term right here, minus vs over r1 brought to the other side. I then do the algebra here. And at this point, it's not quite yet in standard form, but it's close. If I look at this here, I now have the equation in this form. Parker, I want a 1 here. So I'm going to multiply everything by the reciprocal of this. I multiply everything by the reciprocal, and that's what I get. It looks messy, but it really isn't. God bless, Jerry. So I look at this and say, great. Now, Michael, help me out.
How do you know that 1 over r1 plus 1 over r2 plus 1 over r3 equals that?
Right. So Michael, help me out. Your question. So how do I know what this is? I find the common denominator, which is,
That makes sense. Like all 3 times.
I find the common denominator, which is r1 times r2 times r3, right? And then I say r1 goes into this common denominator r2 times r3 times. And I multiply it by 1. So I get r2 times r3 plus r2 goes into this common denominator, r1 times r3 times. And I multiply it by 1. So I get r1, r3. My two colleagues, Michaels, am I doing okay? And then the last term is r3. R3 goes into the common denominator, r1 times r2 times, and all of that times 1. So I get r1 times r2. I think then the rest is just rearranging terms. We're good? Okay. So now I look at this. Now, my colleagues, a word of warning or a word of advice. I saw a number of people today during my office hours, so this is fresh in my mind. A number of people on our exam 2 were thrown off the mark because I asked the next couple of questions differently. Please look at exam 2, either version, because on a problem like this, I didn't ask the questions exactly the same. So make sure you can do exam 2 from this semester, the problem on first-order differential equations. Just make a little note of that. All right? Now, in this form, I asked what I would consider the traditional questions. All right, without even looking at the next sheet, what's the time constant? Where would I find it? Michael? Right. Whatever's in front of the derivative when I have a 1 in front of the non-derivative. Great. Michael, let's go 2 for 2. You can do this. What's the steady state solution or the final value?
It is the thing on the right.
That's right, the right-hand side. What would be going 3 for 3? Then we'll stop. I'll let you off the hook, but you're doing great. How would we get the homogeneous? What's the form of the homogeneous solution? No. Did I tell you my first name is Kevin? And I was named after an Irish saint? K-E. First two initials of my name. And then was S-T, right? K-E to the S-T. Remember I said Saint Kevin? But we found out that S is always negative, right? Good. So what we get, Michael, I knew you'd get it. I knew you'd get it. So Michael, here we go. The time constant. Boom. Homogeneous solution, Ke to the minus T over tau. Boom. Particular solution, right-hand side. We did it. We did it. So Tara, we're through part D already. That wasn't bad. All right. We're doing okay? All right, so I'm hearing that someone in the audience wants me to scroll up. No need to rewind. I'll go back. Here. Time constant, what was in front of the first derivative. Homogeneous solution, Ke to the minus T over tau. For t greater than 0, and tau is given in part B. Lastly, particular solution, right-hand side. Now, with that in mind, determine the complete solution. All right, so the complete solution is the homogeneous plus the particular. Trick is you got to solve for K. And to solve for K, Tiger, what do we need if we want to solve for K? Perfect, Tiger. We need the initial condition. Perfect. All right? So, I start out by saying something here, that we need the initial condition. Now, my colleagues, I want to take this a little slow. Last time hearing it, I want to make sure you're comfortable with this. We need the voltage across the capacitor at T equals 0 plus. As Tiger says, that's the initial condition. Now, since this is the voltage across the capacitor, so Michael, since it's a voltage across the capacitor, it doesn't change instantly. So that means the voltage across the capacitor at T equals 0 plus is the voltage across the capacitor at T equals 0 minus. Now, you might be saying, why is this important? Here it is. We need to get the voltage across the capacitor at T equals 0 plus. Alexis, that's when everything is changing. But it turns out the voltage across the capacitor is not changing. Turns out the voltage across the capacitor at T equals 0 plus is the voltage across the capacitor at T equals 0 minus. And what do I know about T equals 0 minus? Things have been that way for a long time. And if I have things being the same way for a long time with a DC input, what's a capacitor? Open. Perfect, Tara. What's an inductor? A short. So now it's a lot simpler to solve the problem at T equals 0 minus than T equals 0 plus. So what I now do is I draw the circuit for T equals 0 minus. Now let me stop. Let's go back. Let's go back to the figure. At T equals 0 minus, and I'm thinking of my colleague who came to me today during office hours. At T equals 0 minus, switch 1 is open. Doesn't close till T equals 0. T equals 0 minus is before that. So none of this on the left matters. I have this capacitor. Oh, switch 2 is still closed because it doesn't open till T equals 0. We're looking at T equals 0 minus. I have a resistor, an inductor, a resistor. So I say to myself, wait a minute. This has been in this position for like a long time. I'm saying at least 5 tau. So what do I know? Well, actually, a long time. Let's just, because this is a second order system. Let's say it's a long time. The capacitor is open. The inductor is a wire. And what we want to get is the voltage across the capacitor, which is the same as the voltage across R4. So redraw the right side of that circuit. The capacitor is an open circuit. The inductor is a short circuit. And so there's no current going through this capacitor. So what I have is another REQ. REQ is R4, R5 over R4 plus R5. So what is the voltage across the capacitor? It is going to equal, and Parker, by the way, here I think it's best just to write out REQ. It's so easy, right? Because you're going to have to write it out anyway. So this current, now the current from the current source goes through REQ. And we want the voltage across REQ. So it's I times R. Where do I have that here? I times R, using Ohm's law. So now I know the initial condition for V sub C at t equals 0 plus. It's R4, R5 over R4 plus R5 times IS. Now, next thing. This is the equation. That's the complete solution. The homogeneous, k e to the minus t over tau, plus the right-hand side. The only thing I don't know is k. So what do I now do? Michael here on my left, you know. We're going to say set t equals 0. And the left side of this equation is equal to this. Because that's the value at t equals 0. And we're going to set this value of t equal to 0. That's all what's done on the next line. So we say V sub c at t equals 0 plus is what we just derived. That equals k e to the minus t over tau, which is 0, plus the right-hand side. Solve for k, boom. We now plug everything in. V sub c of t is k e to the minus t over tau plus the right-hand side. We solve for k. I just write down here, Parker, tau is given in part B, and this equation is valid. This is very important for t greater than 0. Michael.
Could you just go through the steps one more time? You don't have to explain in detail, just go through the steps.
Got it, Michael. So, Michael, the voltage across the capacitor at t equals 0 minus is the same as t equals 0 plus. That simplifies life. I redraw the circuit. The capacitor is open. The inductors are short. I combine the resistors using REQ. And the current now from the current source is going through that one resistor, the REQ. Ohm's law says the voltage equals R times I. I now jump down here and say, this is the equation, the homogeneous plus the right-hand side. I now set this equation equal to the initial condition at t equals 0 plus. So at t equals 0 plus, this is the initial condition we just solved for. And that's equal to k e to the minus t, but t is 0, plus the right-hand side. Solve this for k, and I get this. And then the last thing we do is we plug it in, and we've gotten everything complete. Michael, how did I do? Okay, good. All right. So that now gets me the full solution. All right. We're up to part F. A lot of parts, Tara, so far, huh? So six problems is okay if we have multiple parts? Yeah. I don't want you to be disappointed. All right. So, my colleagues, Jing, am I blocking your view here? No. You're good? Okay. So I say, look, let's simplify the algebra, because I'm going to ask you to do something here. Define the constant in the homogeneous solution to be k. So you don't got to write out, Parker, the whole big thing anymore. And define the particular solution to be k1. Okay? So notice what I write. V sub c is now ke to the minus t over tau plus v plus k1. We don't have to worry about the values of k and k1 because Alexis, we've already solved it. And it would be messy and cumbersome to write, Brittany. All right, determine the time it will take the capacitor voltage to reach X% of its final value. This is very similar to the problem we had on exam 3. Or no, exam 2. About how long does it take to reach 90% of the final value. Here I'm saying how long does it take to reach X% of the final value. What's the final value? Perfect, Parker. That's the key. The final value is K1. That's the particular solution. Michael, if we let t go to infinity, this term goes to 0. So the final value is K1. So I come down here and say, OK, we want to reach X% of the final value. X% of the final value is X over 100 times K1. Now, we want to determine the time it takes for V sub c to equal that quantity. So what I do is I set the left-hand side of the equation. See up here? It says V sub c of t is ke to the minus t over tau plus k1. I want V sub c of t to be X% of the final value. That's X over 100 times K1. And this has to equal then ke to the minus t over tau plus K1. So I want to solve for t. So Tiger, I'm thinking eventually I got to take the natural log. So I look here and say, I subtract K1 from both sides. I do a little algebra, take the natural log, and I get this expression here. And that's it. I'll give you a moment to look at it. Let me know if you have any questions. My colleagues at home, we haven't left you. We're still here. People are just looking, checking, making sure they can follow it. How do we do on all of this? Tara, that might be it for problem 2, I think.
Where did second K come from?
Sorry, Michael?
Second K come from?
Right, the second K came from the fact that the solution, the final solution's a constant. Michael, since we have a first order system, and, this is important, first order and the input's a constant, this is the form of the solution. Where this is the right-hand side. K1 is the right-hand side. Michael, I didn't want everyone to start writing out the right-hand side because it was a big bunch of variables. So let's just call it K1. So ke to the minus t over tau plus K1 is the standard form for the solution to a first-order differential equation with a constant input. We're good? Okay.
So you're saying K1 equals a particular solution?
Yes, perfect, Michael. K1 is equal to the particular solution. All right. All right. We're up to problem 3. So far, so good on the first 2 problems? All right. Oh, my colleagues, problem 3. I don't even think we have to go over it. I really don't. All right. This is from exam 3. Let's take a look at it. Determine a steady state voltage V1. Use nodal analysis. Tiger, I think we're probably good on this. This is probably the freshest in your mind. I think we could probably say you can look at this on your own. Am I being fair if I say that?
Yeah, let's do that.
Okay. sure? We're good, Alexis? Okay, so we just use nodal. Here, let me just say it, and then I'll stop. I'll just say the first equation. V1 minus 10 at an angle of minus 45 over 10. Then V1 over 10 minus J10 plus V1 over 10 plus J10. And now the current source goes in, so it's minus 5 at an angle of 45 degrees. And you can solve it from there. We're all good? Okay, so we'll say that that was a quick problem to go over. So it's all worked out, my colleagues. The whole thing is worked out, and you can do it. Okay. I'm wondering how you feel about problem 4. Again, problem 4, let's just take a look at it and make sure you're okay. Problem 4 is real and reactive power, which we just had on exam 3. So I give you the value of V1, and I then ask you for the real and reactive power, perhaps from the source, and the power going through the different units. Okay? Let's just make sure we're okay on this. Can I spend just 1 or 2 minutes on this to make sure you're all right? And then you can let me know. So I'll give you a moment. I see a couple of colleagues just writing this down. After this, there's just 2 more problems. But my colleagues, don't forget to do a second order problem to make sure you're ready for the final. In the modules, forgive me, the second order problems are in the, we discussed them in the lecture notes, but the best place to find them, Jonathan, are in exam 2. Okay. So if you look up exam 2 from this semester, both versions, I think you got 2 good examples of second order systems. Does that help, Jonathan? Great, thanks. All right, so my colleagues, let's look and see how I would solve it. Determine the current, says determine the reactive power delivered to the capacitor. So what I do is I determine the current through the capacitor. We're told that we have this much voltage across that branch that has the capacitor in it. And if you look at your solution, at your drawing, Parker, help me out, that was 25 minus J25. So we had a 25 ohm capacitor in series, 25 ohm resistor in series with a 25 ohm capacitor. And we then find the current, and how do I then get the reactive power? I RMS squared times the reactance of the capacitance. Couple of things to keep in mind. Alexis, I know you know this, but it's I RMS, so it's the length of the vector divided by the square root of 2. And when you have reactance, you drop the J, but you take the sign. So it becomes minus 25. And we get a negative reactive power. My colleagues, if you would like me to go slower through this, I will. There's also, you can solve it using voltage division. I'll let you look at that here. You can solve it voltage division on your own. Determine the reactive power delivered to the inductor. So let me just go back. The inductor is right here. So what I'm going to do is I'm going to take V divided by this series impedance, which is 25 plus J25. So this voltage divided by 25 plus J25 will give me the current. I then use I RMS squared times the reactance. So just to go back to that. I is V over Z. So we have this here. So it's again the voltage divided by 25 plus J25. I solve it and get I. And as I was just mentioning, it's I RMS. So it's I peak divided by root 2, square root of root 2, squared times plus 25. And again, my answer key shows you how to do that using voltage division. Determine the real power delivered by the source. Just as we did on the exam that we had, exam 3. Jerry, I want the real power delivered by the source, so I'm going to solve for the current going through here. And I know that current is 10 at an angle of 45 minus V1 over 10. And I solve for I. And once I know I, which I derive here, I then use the formula that P, the real power is VRMS IRMS times cosine theta. What's theta? How do I calculate theta? The angle of what minus the angle of what? Right, thank you, Parker. It's the angle of the voltage minus the angle of the current. Remember, once again, it's VRMS and IRMS. And that gives us the real power, and I think that takes care of 2 quick problems. Did I go through them okay? All right.
You said there's only 6 questions?
I can tell people are very disappointed.
That's 4 hours.
That's been the general consensus here, that 6 questions is not enough.
That's great.
No, I have to reconsider this. I think last year I added more because I know people were saying there was no second order on the review when I had a second order. So I had at least 7 questions last year. At least 7. At least. Minimum number. Could be more.
Maybe 12.
No, I never had 12. Jerry, you got 4 full hours, Jerry.
For 6 problems.
Right. Well, don't hold me to 6. Last year I had at least 7.
So it's 8.
So, all right. Now, we're up to the last 2 problems, so let's take a look at this one here. This one here I think is a filter problem, and then the last one is the topic we had today in class with digital signal processing. Okay, problem 5. All right, so looks like a filter circuit. So we have R1 and L and R2, and I'm probably going to ask for V out over Vn. All right, so now that we got the circuit, it says here, derive an expression for the transfer function. Now, I mentioned you don't have to put this into standard form because it's a little awkward. It requires a little bit of algebra. So I say, look, just leave it this way. J times term 1 divided by term 2 plus J times term 3. Just write it in that form. Okay? So that's the general function of the general form of the transfer function. Now, what I do is voltage division. So if you look at your circuit, the thing that I do first is to calculate Z equivalent. Now, Z equivalent. Now, we're familiar with R equivalent. And just as Michael was saying earlier, not REQ, CEQ, right here. So how do I do it? Product over the sum. Now, what's the value of R2 in ohms? R2. What's the value of this, the inductor in ohms? J 2 pi FL. J omega L or J 2 pi FL. So now we go back to my notes and we say, okay, what we're going to do is we're going to take the ZEQ, and notice that's product over the sum, R times J 2 pi FL over R2 plus J 2 pi FL. After a little bit of algebra, very little actually, in fact none, I just moved the R over. This is it here. I now do Alexis voltage division. So it's ZEQ over R1 plus ZEQ times V in. And that gets me V out. Tiger, so far so good? All right. Tara, I see you busy through your nose there. How can I help you?
In the past, we would have L over R. Like, L over R. I'm sure there's like a reason that like, the circuits are different.
Right. The circuits are different because Tara is saying we used to have an L over R. And Tara, that was when there was just one R. This circuit is now different. We haven't even gotten to that part yet, but this circuit is different. So I've added another resistor, which changes everything. Okay? So, so just follow through on the basic principles, Tara. So we use voltage division. And to use voltage division, I first have to get a ZEQ. So let me pause. How do we do? The short answer to your question is L over R is only valid if there's one R and one L. Here I've added a second R, so there's some other factor going on here. Did I do okay? Okay. You sure we're good? Okay, Tara. So what we then have is V out over V in is given by this expression here. So I'm thinking of our colleagues Michael's comment before about just hitting the high points, making sure we got it. What we do is we calculate ZEQ. That was the first step. Then, second step, we do voltage division. Third step, bring the V in over to the other side and simplify. And I get this. Now, some of you have asked me, how do I simplify this? Multiply top and bottom by R2 plus J 2 pi FL. That cancels it here. That cancels it here. And what I get is R1 times R2 plus J 2 pi FL. Okay? So now, we have V out over V in. It's not exactly the form I had requested. So what we do is we just write this as J 2 pi FL R2. And this becomes R1 plus R2 plus J 2 pi FL R1 plus R2. Tara, you might notice there's something going on here where it's no longer just R. It's something else. So that's why you're seeing something. If I divided everything through, you see something like an L over R. But because there's a second resistor, it's not going to be that, that same form as if we only had one resistor. How am I doing on this, my colleagues? Michael? That's the form that I asked. Michael, if we go back, Michael, right, we could put it into quote-unquote standard form, Tara, but it's going to be a little bit more, see, a little bit more out. So J times something over something plus J times something. If you get it that far, you can stop. And that's what we have. Now, you can continue that to find out what is. It's going to be very similar to an L over R, but it's not just one R, it's two. But I didn't want people to go crazy with that. So, Tara, can I just show you this just for fun?
Sure.
Just for fun. Tara? V out over V in. No, I'll tell you what, it's more complicated than I thought. I thought I could do it in one line. Let's leave it go. This is good enough. Tara, if you're ever interested in a future date about how to convert this to standard form, I can show you, but it takes more than one line and it's not necessary. Okay. Maybe we can, yes, we'll talk one afternoon after D4. I think D4 is Tuesdays and Thursdays, if I remember. From 4 to 6, I think, if they keep it the same schedule. So Tara, we'll call it quits. This was good enough. All right. My colleagues. Now, this is like exam 3. Okay? Except I've just asked you, Brittany, to derive the transfer function. But now I say R1 and R2 is 10 ohms. L is 1 millihenry. And this is the input, V in. Determine V out. Now, Alexis, the key is, since the transfer function is V out over V in, and I already got the transfer function in part A, V out is just V in times the transfer function. So I say, okay, I got to put V in into this polar form. So it's a cosine. Length, the peak, is 100, and the angle is 30 degrees. Perfect. The other thing I write down is what is the frequency. The frequency is 100 hertz. Now, R1, R2 equals 10. That was given. I'm sorry? Ah, excellent, Michael. I'm glad you raised that. Michael is saying, is it in front of the pi t? Not always. Michael, help me out. It's 100 cosine 2 pi ft plus theta. 2 pi ft. What I give you is 200 pi t. So 2 pi ft equals 200 pi t. The pi and the t cancel out. 2f is equal to 200. F is 100. Thank you, Michael. L is 1 millihenry. So what do? Jing, I go back to part A, where I derive the transfer function. And Parker, I now put in the values of L and R, R1 and R2. And that's what I do right here. And this is what I get. Okay, the 2 pi and then the 100. I plug all the numbers in. All right, F is 100. The 10 is the R1, R2. Don't forget, millihenry is 1 times 10 to the minus 3. I then get H of F equals this. So how do I get the magnitude of H of F? I'm hoping you know this, but if not, now's a good time to ask. It's the magnitude of the numerator. This is a vector 6.283 in the j direction. Length, or the magnitude, is this. Jerry, I know how to get the magnitude of the denominator. This is the Pythagorean theorem. 100 squared plus 12.566 squared, square root. I get 0.0623. Now notice, how do I get the angle? The angle of the numerator minus the angle of the denominator. So this angle is 90. It's J pointing straight up. So it's 90 degrees minus the arctan, or tan to the minus 1, of opposite over adjacent. I get 82.84 degrees. So the magnitude is 0.0623 of the transfer function. The angle is 82.84. I now multiply that by V in, which is 100 at an angle of 30. And this is what I get. And I write that in cosine form. This is the peak. That's the angle. How do we do? All right, part C. For this part of the problem, let R1 equal 25, but now let R2 equal infinity, and L is 1 millihenry. So Tara, now I made it the familiar circuit we did in class. Okay, I said let R2 equal infinity. If R2 equals infinity, it's an open circuit. It's wide open. So now, Tara, we have the RL circuit. And I say, derive the transfer function, tell me the break frequency. Okay? So, for R2 equal infinity, the circuit becomes this. Alexis, we're good because R2 is now an open circuit. Again, using voltage division. J 2 pi FL, since that's the volt, I want the voltage across the inductor, divided by R1 plus J 2 pi FL times V in. Now, I put that into standard form, divide through by R1, and we now have standard form. Tara, this is what you were thinking of earlier. We now have this equation here, which we can write as JF over FB over 1 plus JF over FB, where FB is 1 over 2 pi L over R1. And now the break frequency, I give you the value of L, I give you the value of R1. The break frequency is around almost 4,000 hertz. Okay. All right. So at this point, you have now derive the transfer function from the circuit, and I think we're in good shape. What do you think I ask you next? The one thing I haven't asked you so far, what do you think?
Next question.
As part of this question, the Bode plot.
Yeah.
We're going to have a Bode plot. Parker, help me out.
Are you going to ask us to determine whether it's a low pass or high pass filter?
I might. Would you be able to know just from looking at this? Can I quickly go over it?
Sure.
Okay. I'll tell you my secret to how to find out if it's low pass or high pass. Parker, I'm just going to redraw that circuit. So I'm going to hop over here, Jonathan. I'm going to see if I can share with you my secrets as to whether this is a low pass or a high pass. Okay? By the way, Parker, I give you the formula sheets. So by looking at this, you would know if it's low pass or high pass because you've derived the formula just compared to the formula sheet. Okay? But for fun, okay? For fun, plus and minus V in, R, L. Okay, Parker, let's see if I can do this in less than 2 minutes. What's the ohmic value of this inductor? J 2 pi FL. This is R. Okay, suppose V in, the frequency of V in goes to 0. If the frequency of V in goes to 0, that means the ohmic value, the value in ohms of this inductor is 0. It's a short circuit. What's the voltage across a short circuit? 0. V out equals 0. So as F goes to 0, the input frequency goes to 0, V out is 0. Now, V in, as the frequency of the input goes to 0, V out goes to 0. V in, let the frequency approach infinity. Parker, if F approaches infinity, this inductor becomes an open circuit. If the inductor is an open circuit, there's no current flowing. If there's no current flowing, there's no voltage drop across the resistor. So V in equals V out. So V out equals V in. Parker, how did I do? So it has to be a high pass. And the standard form for a high pass filter, I give you the formula sheets. My colleagues, if you have a question as to what I'm going to give you on the formula sheets, look at the posted exams. Okay? This is the standard form for a high pass filter. God bless Jonathan. So if you didn't want to go through that reasoning, you could just say, I got this form. This form is high pass. But that's the reasoning behind it. Parker, did I do okay? Well, wouldn't it be thought-provoking if I gave you an unusual-looking filter with things all around it and then asked you, is it low pass or high pass? That might be interesting, wouldn't you think? Okay. Good. All right, my colleagues. Tiger, I think it's a Bode plot next. Yes, a Bode plot. What is the correct label for the y-axis? H of f, magnitude of H of f in dB. What's the slope of the low-frequency asymptote? 20 dB per decade. What's the slope of the high-frequency asymptote? The high-frequency straight line, 0. What's the value of the Bode plot at a tenth of an FB? Minus 20. Let's see if I can draw all this, Alexis, and make sense of it. I'll come back to those questions. This is the Bode plot of a high pass. Now, I forgot something. I can't believe. Tiger, what should I add to this?
Yeah.
A dot, right? In fact, can I put up the screen? Can I just for a moment put up the screen? Because I can't believe I was so lenient back in my youth. Now I can expect more. Okay? Okay? Magnitude of H of f dB. The x-axis is frequency. This is the break. Parker, since it's high pass, above the break I get out what I put in, which is 0 dB. Below the break, I slope at 20 dB per decade. So that means if I go to 1/10 the value of f of b, 0.1 FB, minus 20. But what do I have here? A correction factor. This is minus 3 dB. And we asymptotically approach it, something like that. That's the Bode plot. All right. We're good? Our final problem. Okay. Problem 6. So this is the topic of our last two lectures, maybe 3 lectures. So I want to make sure I describe this clearly. So help me out. Make sure I do a good job. And a traditional analog filter may be implemented using the following process. Now, I tell you, in this problem, the A to D converter has a sampling rate of 44,100. And each sample is represented by 16 bits. What is the maximum possible frequency at the input to the A to D converter? What's the highest it can be without us having, let me ask it this way, what's the highest it can be and we can still say we're sampling correctly? Remember the theorem, 2 times the highest frequency. So Parker, 44,100 samples a second. That means the absolute highest it can be is 22,050. Determine the number of bits to generate an 80-minute period. The number of bits generated in an 80-minute period. My colleagues, follow the units on this. The units will not let you down. So follow the units. We have 44,100 samples per second. That was given. We have 16 bits per sample. That was given. I want to find out how many bits are generated in 80 minutes. I have to include a conversion factor of seconds to minutes. Look at the units. Sample with sample. Seconds with seconds. Minutes with minutes. I'm left with just bits. So what I get is a huge number. 3.38688 times 10 to the 9th. That's billions of bits. So far, so good? Now, the last part. And I think the next part is the last part. And then we are done. All right. The last part, and this was the topic of our last lecture today. This is the equation for a filter that the digital processor is implementing. Now, I think this is different than the filter we had today. So I tell you that the digital processor implements this signal, this equation. A times y n minus 1 plus 1 minus a times x of n. Now, the parameter a is a constant. The input is 1 only for n equals 0. So the input is 1 only for n equals 0, and y of n equals 0 for n less than 0. All right. You're great to stick with me. Another few minutes and we're done. So let's see if I can describe this clearly, because this is the newest topic, and I want you to get it right. Now, how do you solve this equation? You solve it recursively. That means for me to solve for y of 1, I have to know y of 0. So, my colleagues, here's what you do. Let n equal 0. Start with that. Now we have y of 0 equals a times y. Now, n is 0. So 0 minus 1 becomes minus 1. Plus 1 minus a times x of 0. Now, if I lose you, please stop me, because someone else in the home audience is probably lost. So now I just got to substitute values. Y parenthesis for the parenthesis less than 0 is 0. So that means y of minus 1 is 0. Now, what's the value of x of 0? X at 0. When n equals 0, x is 1. So what I get is that this equals y0 equals a times 0 plus 1 minus a times 1. So what I get is 1 minus a. I say, good. I'm off to a good start, I hope. Okay? Now, for n equal 1, that means what? Now, stop me, my colleagues. I'm plugging in n equal 1. So y of 1 equals a times y of 1 minus 1, that's 0, plus 1 minus a times x parenthesis 1. So I say, okay, what's y parenthesis 0? I found that. That's this. 1 minus a. So I say that y1 equals a times 1 minus a plus 1 minus a times. What's x parenthesis 1? 0. The only time x is not 0 is when it's x parenthesis 0. So this becomes 0. And what we get is a times 1 minus a. So now we've solved 2 steps. I'll do one more, and I think you'll see the pattern. Okay? Here it is now for y equal 2. Y equal 2, here, let me write it down. You're here late at night. I want to make sure you feel you get your money's worth. All right. Parker, how we doing? Looks okay to you? So, I'm sorry?
This one was actually easier than the one in class. Yeah.
Oh, okay. I'm up to n equal 2. So y of 2 equals a times y of 2 minus 1 plus 1 minus a times x of 2. Well, this is 0 here, because x, any x parentheses, the only value of x that's not 0 is x parentheses 1. So that's 0. So this then becomes a times y of 2 minus 1. That's y of 1. That's a outside of 1 minus a plus 0. So what I get is a squared outside of 1 minus a. So if I look, my colleagues, do I see a pattern? I think we do. It's 1 minus a times 1 minus a squared times 1 minus a. I think I solved it even one more time. So I just kept going on and on and on. And the general answer is y of n is a to the n, right? Because here n was 0. So the a to the 0 is 1 times 1 minus a. That's the answer. We've done it. We've done it. How did we do? Done all 6 problems. Don't forget to do a second order problem. I'll leave that to you. And that's it. We all good? Any last questions? Thank you, everyone. I want to thank Jonathan, who's done this now 4 times for us. Jonathan, you're great. I want to thank you very, very much. Jonathan, I think we have 83 colleagues in the sections. Tonight we have about 11, and that's because of you. The other 72 were able to be doing whatever they had to do tonight. My thanks to SITTV colleagues, Jesse, Sean, and Matthew, and anyone else out there behind the scenes. Thanks, everyone. It's been my pleasure. Take care.